quick advice. Look, chemistry is maybe a confusing subject, but it's through practice you'll get the good grades. All right, so I want you guys after this session, practice alone, use some, I don't know, outside resources, we'll supply you with some, and yeah, make sure to continue practicing. Now, if we move on to the next slide, we introduce the table of contents. So to begin with, we will have chapter 1, which is done by Malak, and it's about bonding and isomerism. And chapter 2 will be done by me, which is Alkanes, Cycloalkanes, Conformational and Geometric Isomers. Now, Malak, would you like to start?
Hello everyone. I'm Malak, just like Bara just introduced me. First of all, I would like to congratulate you for finishing your first quiz. Mabruk. Inshallah it went well. I saw some disappointed faces, I saw some happy faces, but whatever it is, take it as a learning experience. Now you know how bio questions are going to be asked, okay? Same thing with chem. You're going to enter not knowing exactly how the questions are going to be asked. So what's better for chem is that there's a drop quiz, okay? So, not saying don't study, I'm just saying, and if you do get a bad mark, that just means you have other chances to prove yourself. Come on? Alright, bonding and isomerism, chapter 1. To go over the atom, how can you tell me the atom consists of what? Exactly. And in the middle we have the nucleus, which consists of our protons and our neutrons. Protons are positively charged and neutrons are no charge. Okay, then you have the electrons, which are traveling or orbiting around the nucleus. Right. Now this is important. Why? They'll probably ask you this question. They will ask you, what the mass of the atom, what makes up the mass of the atom?
Protons plus neutrons.
Yes, not electrons. Electrons here have negligible mass. They're there, but we do not take a part of the atom's mass. But if I ask you for the volume, what does the atom's volume? Electrons. Okay, that's what constitutes most of the volume. Because if you can see from here, the volume is the amount of space it takes, right? Who's orbiting around the nucleus? The electrons. Basically that. Okay, now, this fact, keep it in mind. Engrave it in your mind. احفظوها زي اسمكم, basically. Chemical properties are determined by the electrons, not the protons, not the neutrons, which is important for when we talk about isotopes. Okay? This one, again, also memorize it. Our professor last year really emphasized on it, so understand it, know it. So matter, this is basically chemistry in the macroscopic size. There's macroscopic and microscopic. Macroscopic, when we're talking about mixtures, solutions, stuff like that. Microscopic is when we're talking about the atom itself, okay? So matter can be divided into two things, pure substance and a mixture. Pure substance is what? One type. And mixture is? More than one type, right. Now, let's focus on the pure substance. Pure substance is divided into two things. It's either going to be compound or element. Now, what's special about elements? Simplest form of matter. And the compound is composed of what? Elements, exactly. Now, how can I get a compound from the elements? I need to chemically mix them. Okay, they could ask you a question on how can I turn an element to a compound. So what do we say? Chemical reaction, okay? Same thing, if I want to reverse a chemical reaction, can I do a physical reaction to reverse said chemical reaction? Exactly, so it's also going to be another chemical reaction. Now we go on to the mixture, which is again more than one type of substance. We have homogeneous, heterogeneous. Now what's homogeneous? One phase. It means I can either just see a liquid, just see solids, or just see gases. Heterogeneous, I can see more than one. For example, if I tell you, if I add salt to water and I mix it up, is it a homogeneous mixture or a heterogeneous mixture?
Homogeneous.
Hands. Homo, okay. And if I put sand in water, is it homo or hetero? Hetero. You understood this part. Okay, now the layout of an atom, okay? So the big letter is what? The element. It can be one letter, it can be two letters. Now if it's two letters, the first letter is capitalized, second letter not capitalized. This is important because they could give you a list in my multiple choice. They could give you, for example, CO, both of them are capital, and then CO, one of them is capital, one of them is not. Which one is the correct one?
C or cobalt. C and small O.
Exactly, because one of them is what? Carbon monoxide, and one of them is an element. Okay, so focus on that. Now, bottom number is my atomic number. What's my atomic number?
Number of protons.
Number of protons. Or electrons, exactly. Now, unless there's nothing at the top side here, it means my charge is 0. It's a neutral atom, exactly. So therefore, my proton number is exactly my electron number, okay? Now see, the top number is called the mass number. And what did we say the mass is? Proton and neutrons, exactly. So if they tell you find the number of neutrons, what do?
Mass number
Exactly. You just subtract the atomic number from the mass number, okay? Okay. Now isotopes. Isotopes is basically one element. It just has different personalities in a sense, okay? It has like a personality, you get what I mean basically. For example, lithium, right? It's still the same element, it's lithium, right? It's gonna have the same chemical properties, it's gonna have the same physical properties. Why does it have the same, why does this, and this have the same chemical properties? Exactly, same number of electrons. What changes?
Neutrons.
Number of neutrons. Sorry. Alright, number of neutrons. Next one. Okay. Now when we name isotopes, usually what we do is we put the name of the element and then the mass number. So, for example, carbon, which is a common example. We have carbon 12, which is our normal one, right? Then we have carbon 13, carbon 14. This applies for all elements, except for hydrogen. Hydrogen has specific names that you do need to know in case they ask you about it, because our doctor did emphasize on it. Okay, so for example, hydrogen 1 is just hydrogen, okay? Hydrogen 2, deuterium. How many neutrons are going to be in hydrogen 2? 1. How many neutrons are going to be in hydrogen 3? 2. And what's the name of hydrogen 3? Tritium.
Hydrogen 1 is also called protium.
Yes, but usually they just could take it as hydrogen. Okay, now for the periodic table. How the periodic table is divided into groups and periods. Groups are the horizontal line or the vertical line? Vertical line. So this is group 1, group 2, 3, 4, all the way until 8. Now what's special about group 8? Noble gases, they're inert. Why are they inert? 8 electrons. So that means they do not react at all. Okay? They're stable, they don't want to. If you're stable in your life, why would you want to ruin that? Alright? So that's what it means basically. Now, now the periods. It's the horizontal line. Alright? Now a special thing about groups in all of these elements have 8 electrons in the outer shell. So if I tell you if I have something in group 2, how many electrons is it in the outer shell? 2, exactly. Now this one, they don't really ask about it, but do keep in mind, is how do you do, what's the difference between a metal and a non-metal using your naked eye to view them. So these are some characteristics. For example, we all know what metals look like, right? So we know that they're good conductors, it's high melting point, high density, high boiling point. What does malleable mean?
Changes shape.
Exactly, and what does ductile mean? Wires, okay? Know the definitions of these two words. Okay, now to atomic models. Obviously, the atomic model we know today was not always there. At the beginning, they thought it looked like a watermelon. Okay, this was Thomson's atomic model. He said his theory was it's just space, and then the electrons and protons are divided equally. No neutrons whatsoever. Hello, we know that we do have neutrons, and they're not scattered everywhere through it, right? The second one, then, we had Rutherford. Rutherford did an experiment. This is for your general knowledge. Don't think they ask you about it, but just because the doctor mentioned, I will mention it. He did this experiment where he put alpha particles, threw them through a gold sheet. He saw 3 things, A, B, and C. In A, he saw some alpha particles went straight through. What does that tell you?
Most of the atom is empty space.
Exactly. Most of the atom is empty space. So this contradicted the previous theory. The previous theory was what? That they're all scattered everywhere. There's no empty space. So this contradicted the other one. The B1 is that it deflected a little bit. What does that tell me?
There's a charge nearby.
Exactly. And then C confirms that everything is centered where?
The nucleus.
In the nucleus. Then we have Bohr. Bohr said that, so this is the energy sublevels that we know, right? However, his theory did not continue long. Why? Because this only proved that each subshell has one electron. And do all elements have only one electron? So it was not valid for the rest of the elements. So we completely we took this idea and we built up on it basically. Now, how do you arrange electrons? Like we said, electrons, although they're orbiting, they're not just orbiting randomly, right? They're put into energy levels. Okay, the energy levels will be 1, 2, 3, 4. Go to the next. Think of it as an apartment complex, basically, right? This is the nucleus right here. This is energy level 1, shell number 1, number 2, number 3, number 4, number 5. Okay? In each level, you have a room, right? So for example, here I have only in my first level, how many subshells am I going to have? 1. In my next level, I'm going to have 2, and then 3, and then 4 is the maximum number of rooms I can have, right? Okay. Now, if I have in S, how many orbitals am I going to have? 1 orbital. And in P, how many orbitals am I going to have? 3. And in D, how many am I going to have? 5. And in F, how many am I going to have? 7. Exactly. They're not really going to ask you about F, but just for extra knowledge. And each orbital, how many electrons can I put in each orbital? 2. Maximum of 2. So if I tell you how many electrons are going to be in the first energy level? 2. And if I go to number 2, how many electrons are there?
8.
Exactly. Now we have 3 rules when you write electronic configuration. The questions they usually get is they give you an element and they say which of the following electronic configurations is correct. So you have to follow these 3 rules. First of all, it's Aboudraz principle. You need to put them in increasing energy order. But there's a catch. Every time you solve a question, I would advise to write out the levels like this. Why? Because if you see the arrows at some point, what you would write logically is 3S, 3P, 3D, right? And then 4S, 4P, 4D, 4F. That's not true. After the 3P, 4S comes before 3D. So make sure, because sometimes they switch these two and a lot of people got a mistake on that. So every time you solve a question, like I said, try to write out this, okay? The second principle will be Hund's rule. So right now I'm writing the orbitals. I'm trying to place the electrons. When I'm placing the electrons, I cannot put 2 electrons in one orbital مرة واحدة. Why is that? Repulsive forces between the electrons. So if I put 2 of them, أتحسهم مع بعض, I force them with each other, they're not going to stay with each other, right? So when you're writing it, you put 1, 1, 1. Okay, this is really important. So many questions are going to be asked about this. It's going to stay with you in the quiz, midterm, and final. Okay. The third principle is Pauli's exclusion principle. Okay, the electrons must phase the opposite direction. Similar to the previous one, how I said they can't be together, but at some point we're going to have to force them together, right? When we force them together, they have to face the opposite direction for minimum repulsive forces. Okay, is that understood? Okay, so we've already went through this. You guys know how many orbitals in each subshell. And these are just examples. Okay, now to make sure what the electronic configuration you chose is right, this is an easy way to check. If I give you, for example, oxygen, you wrote your configuration and you ended up with a specific letter. For example, you ended up with P. How are you going to check if it's correct or not? Basically, this part of the periodic table, we call it the S block. So what all of them, when you write their electronic configuration, they're going to end with S, all right? This part, you're going to end with P. That's the P block, okay? This middle part, D. So no matter what, just a quick check. If you don't have time to rewrite it, just check. Where is my element? If it's in the P block, P. D block, D. And then the S block, S. This one is the F, but like I said, they don't really ask much for it. Now there's 3 ways to write electronic configuration. We have the long way, right? Which is writing out every single subshell found and every single electron, right? You have this way, which is the short way. Basically, here we use a noble gas. So, can you write this? For example, if I was to write the electronic configuration of aluminum, right? But I don't want to write out the full thing. What can I do? I look at the period above. I see if there's a noble gas. I have neon. How many electrons does neon have? 10. So when I continue to write the electronic configuration for aluminum, do I have to write out the first 10 electrons? No, I just continue with the 3. Now, a common trick they do on you in these questions is that, for example, they can give you aluminum and then they put argon instead of neon and then they put the 3 electrons. Is that correct? No, so focus on that. Read the questions properly. So many people got mistakes because they didn't read the question properly. And then the last way is showing the actual orbitals, right? Now, we have 2 exceptions when writing electronic configurations, which is with chromium and copper. Memorize these, they will definitely ask you about one of them, okay? So, for chromium and copper, basically the rule they follow is, an atom would rather have a half-filled subshell than a partially filled subshell. And this is for the case of chromium. In the case of copper, the atom would rather have a fully filled subshell than a partially filled subshell. Think about it. You have 2 bags filled with coins. One bag it's nearly full, it just needs 1 more coin to be full. And then you have a bag that just has 1 coin. Would you rather have 2 bags or take the coin, put it in the bag that's full, and then just take 1 bag? Take 1 bag. So that's what the atom is trying to do. It's trying to make itself more stable. So what does it do? For chromium, it has 4s2 and 3d4. So what is it going to do? It's going to take an electron from 4s and it's going to put it on its 5th orbital. So the electronic configuration is going to be 4s1, 3d5. Okay? Now for copper, it has 4s2 and 3d9. So what is it going to do? It's going to take an electron from 4s and it's going to put it in the last orbital to get 4s1 and 3d10. Memorize this, they're going to ask you a question about it. This is just some more examples about writing it with the noble gas. Okay, I asked some of you if the doctor went over a configuration of ions. I think Dr. Alisan did not go over it. He didn't? Okay, so I'll explain it. So it's just simple. You're writing a normal electronic configuration, but you just need to keep in mind the electron that's missing or the electron if an electron is taken away or added, right? So for example, if I have Zn2 plus, so did I gain 2 electrons or did I lose 2 electrons? I lost 2 electrons. Where am I going to take it from? Am I going to take it from my 3D or from my 4s?
4s.
The outer shell, which is 4s. So now I have an empty 4s subshell and a full 3D, right? Same thing here with the copper. Now if it was negative, if I gave you Cu2 minus, for example, gains 2 electrons. So what am I going to do? Add to it 2 electrons, right? Now for Lewis symbols. Lewis symbols is going to follow you throughout all of organic chemicals, no matter what. It's just going to stay with you, okay? So, like I said, the groups, it just shows you the valence electrons in each element without drawing every single electron found in said atom. It just simplifies things. Okay, now we go to bonding. We have 2 types of bonding, which is what? Covalent and ionic, right? Ionic means there's a complete transfer of electrons from one ion to another. But for covalent bonds, they're sharing the electrons. Okay? Now for ionic bonding, from the name ion, what is an ion? An atom that has a charge, right? So an atom is an atom or molecule with a net electric charge due to loss or gain of more electrons. So obviously, if I have an ion, what bond is it going to form? Ionic bond, exactly. What am I going to get from the ionic bond? I'm going to have a positively charged ion and a negatively charged ion. What do we call a positively charged ion?
Cation.
Cation. What do I call a negatively charged ion?
Anion.
Anion, exactly. And this type of bond is formed between what and what? Metal and non-metal. Now this ionization energy and electron affinity, this is really, really important, okay? know what the trend is, they will ask you a possible question, or a question they asked us is what is the trend in ionization energy from left to right? Okay? So if I ask you that, what's the ionization energy from left to right? Increases. And then from up to down, decreases. Does anyone know why it increases from left to right? Exactly. And then it's more difficult if I have more electrons. I'm not gonna want somebody to steal the electrons from me, right? So it gets harder. The more electrons I have, the more attracted they are to me, right? So what's ionization energy? It is the measure of difficulty in removing an electron from an atom or ion. Now we go back to the ionic bonding. We said we have a positively charged ion and a negatively charged ion, right? The positively charged ion, is it going to be the metal or the non-metal? The metal. Why is it going to be the metal and not the non-metal?
Because they have low ionization energy.
Raise your hands.
They have a lower ionization energy.
Lower ionization energy. It's less difficult to remove an electron from a metal than a non-metal, okay? Now electron affinity is, just understand the meaning of it. The amount of energy released when an electron is added to a neutral atom. It follows the same trend as ionization energy, okay? Any questions? Yeah. And metals become cations, they become positively charged because they have a lower ionization energy. They're more willing to let go of the electron than non-metals. Non-metals want the electron, they don't want to lose the electron. Okay? Now for covalent bonds. We said covalent bonds do what? Share electrons, exactly. So, and this covalent bond forms between what and what? Non-metal and non-metal, exactly. Now, why do they share instead of a complete electron transfer between them? High electronegativity between both of them. So none of them want to let go of this electron. So what do? They compensate for that fact and they share the electrons between them. Okay? Now bond energy. From the name itself, bond energy is the energy needed to break a mole of covalent bonds. Alright? The amount of energy obviously depends on the type of bond I'm breaking. And the energy I need to break a single bond, is it going to be the same amount as a double bond? No. Is it going to be the same amount as a triple bond? No. And between different elements, it will differ. Do you need to know these numbers? No, you do not. If they want you to calculate something, they will give you the numbers. So don't memorize any numbers. Now for the bond length, it's the distance between the two nuclei. Because the bond doesn't start from one end of the atom to the other end. It starts between the nuclei. Now the difference in the bond lengths between ionic bonding and covalent bonding. Ionic bonding, you add the radii of the two atoms. Why? Because we said they're not sharing, they're just standing beside each other. Okay? But for covalent bonding, we said they're sharing. So can I just add the radii? I cannot add the radii. So the equation for it is you're going to take, for example, I have HCl. I want to calculate the bond length, right? I take the bond length of HH, which is 0.74. I take the bond length of ClCl, which is 1.98. I add them together, I get the average, I divide it by 2. Now, is this number an accurate number? No, it's an estimate. Obviously, other factors are being involved in this, but we always get the estimate. This is what is required from you. Again, don't memorize any numbers. If they want you to calculate something, they're going to give you. Okay? Any questions?
When we have a corner bond and a non-corner bond, which one has greater bond?
What do you mean?
When you have a non-corner bond, like let's say carbon-carbon and carbon-chlorine, which one has greater bond?
Polarity, you mean? Are you talking about the polarity? Obviously, the ones with two different elements. Because if it's carbon-carbon, it's the same. But if I have carbon and chlorine, one of them is going to be more electronegative than the other, right? Yes, it will be weaker, but are you asking about polarity or the strength of the bond? Bond length, it will be longer. Why? Look at the numbers here, right? You gave me CCl, right? CCl. You look at CC and then ClCl. Now we know that chlorine is a bigger atom than carbon, right? So the bond length will be longer. The longer the length of the bond, the weaker the bond, right? Is that your question? Okay, now to draw the Lewis structures of bonds. It's pretty straightforward. There's not really much explaining to it. If you see a line, what does that mean? A bond. Two electrons, or there's two electrons between them. Okay, now carbon. Carbon in this whole organic chemistry course is going to be the elements you're going to be talking about the most. Organic chemistry is based around the atom, carbon, okay? So just some facts about carbon. It can make up to 4 covalent bonds. Why can it make up to 4 covalent bonds? 4 valence electrons. Can it make a double bond?
Yes.
Can it make a triple bond?
Yes.
Yes. Now obviously, going back to bond lengths, the bond lengths. If I have a single bond and a double bond, which one is going to be stronger?
Double.
Double bond. Why? Exactly. Okay. Now, this is obviously, you're going to go into more details in later chapters, but just a general idea. What's a radical? Not a single electron, it has an uneven number of unshared electrons or unpaired electrons. So if you see here, basically, in ethane, after we break it with heat, because
Go ahead.
now, for example, for methane, when I break it with heat, you see how we were sharing 2 electrons between them? When it breaks, now it has 1 electron each. We call these radicals. Now, for now, this is all you need to know about this. Later on, you're going to learn about it more, but so far, this is all you need to know. Do you understand this part? Okay. Now, and I said if something is electronegative, it wants to it wants to receive electrons, right? So what if I say something is electropositive? What do I mean by that? Give electrons, opposite of electronegativity. Okay, so if you see the word electropositive, it's not a new word to you. It just means opposite of electronegative. Okay. Now, if we have a horizontal line in the periodic table, I'm going from left to right. More electropositive. No, sorry, more electronegative, sorry. From left to right, it's becoming more electronegative, right? And then if I'm going down, from up to down, less electronegative, exactly. Okay, now polar covalent bonds. So this is basically just covalent bonds with extra steps, in other words, okay? So, again, electronegativity is what? The ability of an atom to attract a bonding electron to itself. Basically, this polar covalent bond is found when you have 2 different elements and you have a bond between them. Just like somebody who asked right now, if I have C and Cl, or for example H and O, one element is going to be obviously more electronegative than the other. So the electron is going to be attracted to who? The more electronegative one or the less electronegative one? More electronegative. So how are we going to present it with an arrow? One side is going to look like a plus sign. What does that mean? Less electronegative. And the one with the arrow, what does that mean? More electronegative. So the electron shared between them, is it going to be closer to the O or to the H? To the O, exactly. So what's the trend for electronegativity? Same thing like before. I said from left to right, electronegativity increases. These trends, memorize them, they will ask you about it. Okay? Or they will ask you indirectly, but you will need to know the trend of these properties. Now, electronegativity is a periodic property, not a property of the atoms. Okay? Keep that in mind. It's a periodic property. But when I'm talking about ionization energy and electron affinity, it is a property of the atom itself. Okay?
Why does the electronegativity decreases when going from up to down in the periodic table?
Okay. Basically, when you're going from up to down, right? The number of shells, doesn't it increase?
Yes.
So the electrons become farther away from the nucleus, huh?
Okay.
So the attraction, is it more or less?
The attraction?
Between the electron and the nucleus.
Less because it's...
Exactly, so it becomes less electronegative when I go down.
Oh, yeah.
Got it? Okay. Yes. Periodic property, it depends on its position in the periodic table. You know how I said just from left to right, electronegativity increases. I didn't say, oh, this element has more. I just said, go a certain direction, it changes. But for the property of the atom, each atom, not element, each atom has its own ionization energy. So between ions, for example, the ionization energy is not the same. If I have Cr and Cr+, they don't have the same ionization energy. So it's a property of the atom itself. It changes between them. Understood? Any more questions? Numbers, no. Just know that fluorine is the most electronegative element. That's all you need to know. Do not memorize numbers. They're going to give you the numbers. Okay? Any more questions? Okay. Now, for example, here. They could give you a number, or they basically give you this number and tell you, is it an ionic bond? Is it a covalent bond? And what type of covalent bond is it? Is it a polar covalent bond or a non-polar covalent bond? Okay? If it's an ionic bond, the number will be greater than 1.9. Okay? 1.9. If it's greater than 1.9, it's an ionic bond. If it's between 0.5 and 1.9, it's a polar covalent bond. If it's less than 0.9, what is it going to be? Sorry, if it's less than 0.5, it's going to be a non-polar covalent bond. Got it? Do I go over it again? Repeat? Okay. If it's less than 0.5, it's a non-polar covalent bond. If it's from 0.5 to 1.9, polar covalent bond. More than that, ionic bond. They could give you the number and say, what type of bond is this? Okay? Everyone got it? Okay. Now formulas, different types of formulas. You always have your molecular formula. Molecular formula just shows you that the elements and how many atoms of that element you have. Okay? Straightforward. But if they ask you for the empirical formula, what you do is basically you simplify it. Simple maths, in other words. So for example, I have the formula of glucose, just C6H12O6. If they ask me for the empirical formula, can I make the numbers simpler? Divide by 6. Divide by 6. If I divide 6 by 6, I get 1. 12 by 6, 2. And 6 by 6, 1. So when they ask for the empirical formula, they're asking you for the simplest formula of said molecule. Okay? Is that straightforward? Sorry? Okay. So I have my molecular formula. When they ask for the empirical formula, they're asking for the simplest formula of the molecular formula. So if I see that I can minimize the numbers in any way possible, I minimize them. Now this means that if I'm going to divide this number by 6, I divide all the numbers by 6. Which one of them 6 and one of them 2 and one of them 3. Alright, so if you're going to use one number, make sure that all of them are divisible by it. Like for example, if I give you C5H12, what's the empirical formula of C5H12?
Divided by 5.
But can I divide 12 by 5? Exactly. C5H12, empirical formula is C5H12. So like I said, if you're going to divide one number, make sure the other numbers there can be divisible by said number. Yes. Okay. Okay. Now structural formula, we have 3 types. Okay. We have the full-on one, which is this one where you see every single bond present in the molecule. Okay. Then we have the abbreviated one, or we're just basically making it smaller. Instead of, you're gonna still see bonds, as you can see. Sometimes you can see the bonds like CH3 bond, CH2 bond, CH2. That's still a condensed abbreviated formula. Or sometimes you can just see letters. When you just see letters, what is that? Abbreviated structural formula or a condensed formula. Okay. So all you do is you remove the lines and you condense them together. You got that? Okay. For line diagrams, you do not label the carbons and the hydrogens. Can you see any carbons labeled here in hydrogens? No, but who can tell me what the formula for this one is?
C5.
Exactly. How did you know? just it came to you as logic sense. That at the end you have 3 hydrogens, in the middle you have 2 hydrogens. How did I know that there are only 2 hydrogens in the middle and not 3? Exactly, carbon can have 4 bonds. So when you're writing the formula, keep in mind how many bonds can this atom hold, okay? All right, now we have a type of isomer, constitutional isomers, all right? For chapter 1, this is only the isomer that's available, okay? Constitutional isomers is basically when, here basically, okay? I have C5H12, right? I can take the branch at the end, and where do I put it? If I put it here, if I basically, okay, if I, for example, this part, okay, sorry. So this part basically here, if I bring it here, so instead it's going to be C, 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 sorry, and then C here. Is that a structure? Is that a constitutional isomer or not? It is. Why?
Same formula.
Exactly. How do you know? Yeah. Exactly. So if I get the longest branch of carbons, it's going to be 4, right? What was my longest branch here? 5. صح? But what if I do this? What if I do this? Is it an isomer or not? It's not an isomer, exactly. Everyone got this part? Yes? Okay. So look, basically, this is my original molecule. Okay? Who asked? Okay. This is my original molecule. If I give you this, is this an isomer or not?
Yes.
Is it or not? It is. Do you understand why? Okay. Look here. What's the greatest number? If I'm gonna try to get the longest chain of carbons, right? This one. Yes. 3, 4, 5. صح? Here, if I get the longest chain, how much is it gonna be? 4. So is it different or is it not different? Different. But what if I had this? Different or not different?
The same.
Do you understand why it's the same? Any other questions? خلاص? Okay, formal charge and Lewis structure. This one is really important. Definitely gonna ask you a question about this. So if you don't understand it, look for videos, practice, okay? How do I get formal charge? How can they get you a question about formal charge? They'll give you a structure of an atom, of a molecule, and they'll tell you which is the formal charge, what's the formal charge of this, okay? What do? If you have a molecule, right? For example, let's take CO2, okay? Okay, here, for example, N2. They gave me this structure, right? Now I want to find what? The formal charge, right? So what do? What's the formula of formal charge? Sorry? Yeah, I can't hear you. Divided by? خلاص, okay. So that's the question they could get for you. Did everybody understand that part? Okay. Now for Lewis structures, what could they do? They could give you more than one structure and tell you which one is the correct one. How do I know which one is going to be the correct one? Okay, and then what do? Find the one with a formal charge closer to 0. Doesn't necessarily have to be 0, but it has to be close to 0. Everybody got that part? Any questions? Okay. This is an alternate way to do it, but if you understand the first way, just ignore this part completely, okay? Resonance. Now for resonance, it basically means that a molecule can be drawn in more than one way. What does it mean? This is usually found when we have a double bond. They found out that the double bond, for example, this is a double bond, is not actually a full-on double bond. This double bond is distributed between this O and this O. And there's another form, it's distributed between this O and this O, and this O and this O. Right? So whenever you have a double bond, expect it to have another way to be written. Okay? It's just switching. Basically, that's it. You don't have to add an extra bond, you're just switching them around. Okay? VSEPR. This is showing you how a molecule will be in 3D space. Okay? Now, what's special about the tetrahedral one compared to trigonoplanar and linear? It's non-planar. This is the only one that's non-planar between these two. Linear, it's all in one plane. خط مستطيل. Trigonoplanar, they're all on the same plane command. All three bonds are on the same plane. For tetrahedral, the three of them, you see the ones in the back? It's a trigonoplanar, right? But this one is sticking out to the front, so is it going to be in the same plane? It's not going to be in the same plane. Okay? Any questions about this? Okay, orbital, sigma bond and pi bonds. Okay? Now, sigma bond can be either a P and an S, giving me a PS sigma bond, an sp3, which is hybridization, we're going to go over that, and an S bond. It can be a P and a P, and an sp3 and sp3. Know the shapes of the S orbital and the P orbitals. The S orbital is what? Sphere. And the P orbital looks like? A dumbbell, exactly. Now, the pi bonds, unlike the sigma bond, you see how the energy in the electron is distributed along the axis? The pi bond is فوق وتحت, up and down. But which one is stronger? Is a pi bond stronger or a sigma bond stronger? Sigma bond. Why is that? Chemistry. Because see, this one, it's along the axis. This one, if I twist it, خلاص, bond is broken. Okay? Hello, you said sigma bond is stronger than a pi bond, right? But why is a double bond? Exactly, that's why a double bond is stronger than a single bond. Even though I said the pi bond is weaker, right? Because in the double bond you have both the sigma bond and the pi bond. So obviously it's harder to break the bond, right? Hmm?
You said in a double bond there's both a pi bond and a sigma bond?
Yes. You have the sigma bond. This is every single bond is just a sigma bond. A double bond, as soon as you have a double bond, you put a pi bond. You got what I meant?
So one is pi and
One is pi and one is sigma. Every single bond, you always start with a sigma bond, and then you add on the pi bonds. Did you get it or no? Sure, I'll explain it after. Okay? Come to me and I'll explain it after. Okay, now sp3 hybridization. Alright? This basically, the whole concept, it's basically composed of one s orbital and 3 p orbitals. Okay? What do they do is basically, this is what happens. You have a 2s and a 2p. The 2s is full of how many electrons? 2 electrons. But we have we have one empty orbital, right? So what is it going to do? It's going to donate 1 electron. But then we have a half-filled orbital. Do we want a half-filled orbital? No. So what do? Bring it up. So now I have an sp3, which is way more stable than what I had before. Do we get the part of how it's made? Repeat it? Okay. So look, I have 2p2 and I have 2s2. I have one empty orbital, صح? Do I want to have an empty orbital? No, I don't want to have an empty orbital. So what do? I take an electron from 2s and bring it up. But then I have a half-filled 2s orbital. Do I want a half-filled 2s orbital? No. So what do? I move the s orbital to the p orbital. So now I have an sp3 subshell. Did you get that? Understood? Any questions about this? Now these points, you don't need to understand what they are, just know what they are in case they ask you. Don't go into details about them, just know what they are, okay? So these are the good points and these are the bad points. Functional groups, go over them briefly. You're going to take each one in details every chapter along the way. So you don't really need to know much information about them, but do at least know how they look like. Alright, I know that a single bond is an alkane, a double bond is an alkene, a triple bond is an alkyne. So just general knowledge on this. No, know them, but don't go into details about them. Don't force yourself to understand what paramagnetism is or spectroscopy. They're not going to ask you that. They're just going to ask, what's a good point? What's a bad point? That's it. Okay? Bad point about hybridization, the theory of hybridization. This is what I meant. This is the characteristics of the theory I just explained. Okay? These just, you can go over them from the PowerPoint. It just explains what each arrow means and what's going on. So any questions before I give the mic to Bara? They can ask you how many the number. Okay, this one. This right here. They can ask you if I have a linear, how many hybrid orbitals am I gonna have? Okay? That's all you really need to know. If you still don't understand it, go over the book. It does help in explaining it. They can tell you which one is a resonance structure of, for example, CO. And they're not going to all be correct. Yani they could do what? They could do C and O, they give you a triple bond. Is that a structure? No. So this is basically how it's going to go. Any questions before I... Yes?
What's SP2 and SP axis?
This one you don't really need to know much into details. Like I said, this table, إذا تحفظوها, you're good to go. For about SP and SP2. The only one you need to know about is the SP3 and why it happens. If you still don't understand it, book. Go over the book. Okay? Any more questions? Sigma and pi? After class, because he needs to go over chapter 2. Any more questions? Right? Did somebody ask, can it be SP4? No? No. Okay. Any other questions? Yes. And the table I told you about, just know it. This one. It's in the PowerPoint, yes. It's in. Functional groups, ما تحفظيهم, just have a general idea about them. لأنه كل chapter بعدين you're going to get a chapter about alcohol, you're going to get a chapter about aldehydes, ketones. Yes, just know the general idea about them. Know what an alkane is, yeah, just basic information. Okay? Any more questions? Alright, thank you guys.
Thank you so much, Malak. Now we're going to start with chapter 2. Before I get into it, I want to give you guys a summary about alkanes. We'll look over alkanes, cycloalkanes, the conformational and geometric isomers, and whatnot. Now you'll see in organic chem, the flow of what all our doctors use is that they start off by showing you the structure, the basic structure, then the nomenclature, meaning how do we name them. So inshallah, in next chapters, aromatic, alkenes, alkynes, you look at how we'll name them, and as well they'll look at how to make reactions with them and what are their products and all that. So that's the flow through all the organic chem course. So, all right, so we start off with types of hydrocarbons. Before I begin, do you guys know what does aliphatic and aromatic mean? Yes. So aliphatic means it's like just a line, so no benzene ring, nothing. Tamam? Aliphatic includes what types? It includes alkanes, alkenes, alkynes. For now, we're just going to focus on alkanes, which is basically one bond. And do you guys know what we call alkanes? Like, there's another name to it. It's just right there. Exactly, it's saturated, meaning it has just a single bond. And when it's unsaturated, that means it has double or triple bond. Exactly. So alkenes, for example, are double bonds, and alkynes are triple bonds. Now, aromatic is the fourth chapter. You don't have to worry about it now, and it includes the benzene rings. So if we move on, before that, do we have any questions about the hydrocarbon classes? Tamam. All right. So the structure of alkanes. Did someone raise their hand? Oh, yes.
So cycloalkanes, are they arenes?
No, cycloalkanes are a class of just alkanes that are into a circle. Benzene, inshallah, when you get into chapter 4, you'll see that they have their own rules, their own forms, and especially that this one is conjugated, meaning it has double bond, then single bond, double bond, single bond, double bond, single. Yeah, cycloalkanes is only just one single bond into a circle. All right. So now the structure of alkenes. Before we begin, you guys know how to calculate a generic formula? So do you know what's a generic formula? Alright, so let's say we have a alkane with one carbon. That means how many hydrogen would it have? Hands. Yes. 4. So we use this formula. Let's try it. Let's add 3 here. How many hydrogens would we have? 8. So I remember like in the first quiz we had a question. He asked us a pretty simple question. He's like, what if in an alkane you had 4 carbons? How many hydrogens would you have? Or he might ask, if we have 10, for example, what's it called, hydrogens, how many would we have? So you understood? Alright, so this is the generic formula. Now alkanes are structured in a way, this is how we draw them. However, this is how they are in real life. Now how we draw them is basically just a C, a single bond to H, for example. Here's methane, we'll get into the naming. C, single bond, single bond, single bond, single bond. Alright, this classifies as an alkane. And it's it's found in the real life. It's like, I don't know if you guys know what a tetrahedral looks like. Basically it's like this. So there's like H, 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 the C bond, and another H to the top. Of course I can't do it with my fingers, but I think you guys get it, right? So it's kind of like this. So H, 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 and then you have a C right here, and then a H to the top. Like a chandelier. You guys know what a chandelier is? Lomba, hey, that's that. This is how it is, and its angle is 109.5. So if you look here, it's 109.5, and this is the ideal angle in what's it called? In a alkane. Now moving on, we have alkanes. They could be either linear, as we discussed, so it could be just a straight line of C's attached to each other, so a chain of just carbons, or branched, meaning it could become like, you know, a tree branch, and maybe from here you get a C, then a C, and then a C. So it makes like artwork. Let me draw it, for example. You have C, H, C. Well, here we have a C. And then we have here H, and then we have, for example, C. So the branched are usually ones that have like extra methyl groups, ethyl groups, just an extension to a regular line. Oh, and also for the structural or number of isomers, I say for alkanes it's tough to calculate, so just memorize the table. He usually asks till 9 mostly. They usually ask till 9. So for this one, just memorize, alright, for CH4 there's only one isomer, that means one shape. C2H6, there's one shape. C3H8, one shape. And then C4, there would be 2 shapes. Any question? It's easier to memorize it, because sometimes they would ask C6H14 and you wouldn't have the time. Because it's like 30 minutes, 20 questions. So you want to, you can't really draw it that fast. So just memorize this table. He doesn't go over 8. Like, put 9 as a maximum. So yeah, just memorize it. Moving on. Alright, nomenclature of alkanes. So do you guys know how to name alkanes first of all? Yes, so what is the suffix of any compound that's alkane? Ane. Exactly. So let's take for example this. Could someone help me name it? I chose you already. Yes. Yes. Hexane. Alright, how did you find that out?
6 carbons, and it's an alkane with single bonds. We have A and E, so hexane.
Exactly. So basically, as she said, we look at the C's, we take the longest chain of carbon, we highlight that chain, and then we add a prefix which is, do you guys memorize it? Methane, ethane, yes. So memorize those and then just add ane to the ending. That's it. That's how you name them. However, it could get complicated when we introduce functional groups or groups like those. Now for alkanes, they might just introduce like chloride or maybe methyl groups or ethyl groups. So can someone help me name them? If you don't know how, no problem, we'll work together. Yeah. Hey. All right, let's do step by step. Let's count the number of carbons first. All right, so 1. All right, so 1. Now this dot represents a carbon, so 2, 2, 3. All right, there's a 4th one. Now we said we need to choose it as a continuous chain. So what is the longest? So 1, 2. Exactly. So it doesn't matter. You could choose it like this, or you could choose it like that. Do you get me? All right. Now let me just erase it. All right. So let's say we chose this one because it's easier to identify. Now, what do we do with those extra groups that are to the side? What do we do with it? All right. Yes. We start with chloro. All right. So how here, because it's even, it's just in the middle. We number them 1, 2, 3, or even if it was 1, 2, 3, we get the same thing. So let's say, all right, we found, all right, we numbered them. We found the longest chain. What do we do next? Name it. Now, how do we name it? Wait, one person. Yes.
According to the least number of components, so like we go and see which carbon has the least number of carbon that has CN or metal.
All right, and then, all right, let's say 2. You mean like 2, right?
Yeah.
Yes, second carbon. She means that 2 here, for example, we do it alphabetically. So 2, chloro, 2, methane, methyl, sorry, yes, and then propane, yes. Propane. All right. So you get this structure, right? And you get the naming. Now we'll move to a bit harder one. So we're just gonna zoom into it. All right. So are you guys familiar with this line structure? All right. You want to answer? Yeah. So again, you said 2. So you said 2. Bromo. Sorry. 7. Dimethyl. Octane. Now, who agrees with this answer?
No one.
What's it called? By the way, I did a similar mistake in my midterm. It's still alright. Let's see someone of you who can help. I saw you raise your hand.
Yes,
Alright.
we have 2 brushes here for metals, so we have to
Alright.
start from the left. Row, no, let's put 2, 2.
2, 2.
Dimethyl, but we have to put the row before now.
Hey, throw you guys. ركزوا جماعة. Hey.
2 dimethyl.
Dimethyl.
And 1, 2, 3, 4, 5, 6, 7. 7 bromo is before it. Before it.
Alright, 7 bromo.
Not here, not here.
Before it.
Added to
Yes.
1, 2, 3,
Correct.
4, 5, 6, 7, 8.
And then octane. Now, who agrees with this? Yeah. So, yes, this is the correct formula to this structure. And just be aware from naming. Sometimes, all right, this is alphabetically correct that bromo is B and methyl is M. However, we look at which one has more branches to it. Understood? So, for example, this one has 2 methyl in the second carbon. So that's why we chose it. We chose it instead of the bromo. You understood this aspect of the naming? Alright, moving on. So we move on to the physical properties and intermolecular forces. Now, for the intermolecular forces, I made a small mind map or concept map that could simplify it. So, what are intermolecular forces? Do any of you know what are intermolecular forces? Hamza. Yes, so it's within the molecule itself. And what are its types? We have hydrogen, dipole, van der Waal. Now, can someone explain to me what is hydrogen before we look at it? Hydrogen bonds.
It's the strongest one.
Alright, it's the strongest. What else?
It's the bond that hydrogen forms with carbon, fluorine, and nitrogen.
Let's listen to it.
With carbon, fluorine, and nitrogen.
Not carbon. Oxygen.
You mean oxygen? It's good, yes. Hydrogen, alright, so hydrogen will be in the middle, and then you have oxygen, fluorine. Alright. Huh? Yes.
Hydrogen bond forms when hydrogen is between two high attractive atoms. It forms a covalent bond with one, and the hydrogen bonds with another.
Correct, exactly. So let me draw it out. Alright, so in hydrogen bonds, we have, let's say, O, and then this is carbon chain, hydrocarbon chain. And then we have H, then another O, and then another hydrocarbon chain. So you guys understand how it's formed? So basically we have two electronegative atoms sandwiching a hydrogen. So this forms what we call a hydrogen bond. Now we move on to the next one, which is the dipole. Now, can someone tell me a bit about the dipole? Alright, yes.
The polar can be equal and not.
Alright, true, yes. It's weaker than hydrogen bonds. What else? Alright, what else? Alright, so dipole, as you guys said, is the second strongest, or you could put it as the second weakest. Yes, so one has a more negative, yes, than the other one.
Permanent.
It's a permanent attachment, yes. So the forces arise from the attraction of oppositely charged atoms. So you have a molecule, an atom that is, in general, just negative or more negative than another one. The other one must be positive for it to attract. So this one creates a form of, as you've mentioned, permanent attraction. And these are generally weaker than the H bonding. Now, they mentioned in the PowerPoints the ranges. I'm pretty sure, I don't remember them asking us about it. So don't look into the ranges of kilojoules per mole. It's not that important. Now, general in organic molecules, they result from the presence of C and X. So a carbon and electronegative molecule. This creates the shift of what's called electron change. So for example, one molecule is CX, that makes it more negative than another molecule, which is maybe just a row of carbons. You understood this aspect of dipole? You sure? All right. Moving on, we have the van der Waals intermolecular force. Now, who can tell me about the van der Waal intermolecular force? Yes. It's the weakest one. All right. What else? Is there like? Yes. It's temporary, exactly. And, all right, so let's look into it. The forces arise for the movement of electrons within a molecule. So it's similar to dipole, however, it's weaker since it is temporary. The movement, it does not stay constant. So you might find that it has a portion where it could be strong, then it will become weaker. And then this natural motion can produce an uneven distribution of electrons. Since we said it's included with the movement of electrons, that's why the charge is created, and then there's attraction. But it's very weak attraction, and as your friend mentioned, it is temporary. Now look, the physical properties that come with intermolecular forces are boiling point, solubility, and in general the strength of interaction. Now the boiling points are also dependent on the mass of the molecule. So if the molecule is big, let's say like a big branch, we can show you in the other slide. Yeah, a big unbranched, linear, or aliphatic, it will have a higher boiling point because it has more places to interact. You understood this concept? So if it's branched like this, it will have a lower boiling point. And why is that? Less surface area. So you can see here. You can see here. Here it's just attaching from those two sides. However, this it's like an M. All this is attaching to each other. So it's because of the surface area. That's why the branched ones do not have a lower boiling point than general aliphatic hydrocarbons. Right, and then the solubility is the ability to dissolve into a solvent, and it is depending on the intermolecular force. Yeah, and then moving on. Yes. Yes. All right, a polar bond. Yes.
One is more electronegative, there's partial negative, partial positive. Same molecules have the same thing. So the partial positive is attracted to partial negative. This is attracted.
Yes, exactly. I can draw it in a way you could understand, which is basically, let's say, so this is the partial sign, partial negative, partial positive. And it's within the same molecule, by the way. This is just one molecule. Another identical molecule, since it has one side that's partial negative and one side that's partial positive, as your friend said, since this is partial positive and this is partial negative, it'll make an interaction. You understood this aspect? Yes. And hydrogen bond? Hydrogen bond, this usually doesn't have a hydrogen that's sandwiching between them. The hydrogen bond, as we mentioned, it's an O, and then you have an H. Could be an F, or any other, or O, or N, any other that have the power to take the hydrogen as well. That's sandwiching between two electronegative molecules. Understood it? Yes, I believe they have a list as well in the PowerPoints. So moving on. All right. So the boiling points of alkanes, they are nearly linear with the increasing size and mass. As I mentioned, the more you have carbons that are attached to each other, the more the boiling point. And not attached as in branches, attached as a linear aliphatic hydrocarbon. So since we're increasing the number, the boiling point increases. So I hope you get this aspect. If you have any question, you could ask me. No? All right, so dipole forces are much stronger IMS, so the BP is higher when the dipole-dipole interactions are present. So dipole-dipole, when there's a dipole-dipole force, let's draw the structure again. So negative, positive, negative and positive. This gives it a stronger attraction to boiling point. So when we have a dipole moment or a dipole interaction, this makes it a high boiling point. You guys understood? All right. So we have hydrogen bonding. We said it's the strongest intermolecular force, and their BP are the highest for the equivalent molecular compound. All right. So let's take, for example, 1, 2, 3, 4, 5, 6. All right. So hexane, and then we have this diethyl ester, and then we have the pentanol. So which one has the highest boiling point from those? Exactly. Yes, the one with OH at the end, the one with the hydroxy group. So why do you think it has the highest boiling? Yeah. The hydrogen bond, exactly. So this hydrogen bond right here, it could interact with another electronegative molecule, and it could attach. And this attachment, as we said, is stronger than the other intermolecular forces. However, here we have an O, but why is it not as strong? Because we cannot really make a hydrogen bond here. So, yeah? Exactly. So it's already in a bond with two carbon and they're fighting over their electrons. They don't have space to fight with another one. And there is no hydrogen attached to it. So we can't do a hydrogen bond. Now, and here it's we said that it's a hydrocarbon hexane. Why is its boiling point higher than this one? Why do you think it is higher? You guys have any idea?
Due to the shape, due to the oxygen, this will be bent, while this will have a
Yes. So remember when I mentioned the surface area? So this one may have more surface area to attach to another one of its kind. So here hexane, let's say, we have multiple hexanes stacking on top of each other. And? Yeah, they have van der Waals forces. However, since they have more surface area, so more van der Waals forces is better than just one dipole moment. And since this surface area is smaller, due to its bent shape, it has less boiling point. All right, now here's the interesting part that I heard many of you guys were asking. Before we get into it, you guys know what is the Newman projection and the sawhorse. Do you guys need help in understanding it? Do I draw it? All right. So now, before we start, there is a Newman projection and there is a sawhorse projection. So Newman's projection, it looks like this. It looks like a pie chart in a way. Right? Alright, and a sawhorse looks like this. So in conformers, we know that there are about, let's say, four carbons or two carbons that are just rotating. So we have C and another C bonded together and they're rotating. So two or more carbons that they share a single bond, so they're able to rotate, right? So in Newman's projection, he drew it in this way. CH3, let's say that this is H. This is butane. And they have H, CH3. So the big circle in the back, this big circle, this is the carbon that's at the end. It's the carbon we draw in a flat way, C, and C. This is this carbon. It's attached to CH3, which I show here. It's attached to H, and it's attached to another H. So it's attached to CH3, CH, and another H. You guys understood this? How's it? All right. And then you have the front one, which is this. It's attached to an H, so an H, and it's attached to another H, and it's attached to a methyl group, which is this. Correct? All right, so you guys heard of the staggered eclipse formation?
Yes.
All right, so we have it here. So a staggered formation means that the big groups or any group on the Newman projection or any other projection is overlapping. So let's say that this CH3 gets to this position. This is eclipsed. So here we see that the CH3 and the CH3 both align and are back to back. Yes, we're gonna get to that point. And we see that there's an H and the H that are overlapping. So two H overlapping, two CH3 overlapping, and two H's overlapping. Correct? All right. So this we call eclipsed. And eclipse is less stable since there's a force that is pushing the molecules from each other. You guys know the name of the force? Torsion, yes. Torsion. So due to the torsion, there's going to be a spinning. Jamaat al-Yon. Due to the torsion, there's going to be a spinning. So you're going to see that due to these forces or those molecules pushing at each other, they're going to start to spin. We'll go in a way. So we'll spin. And then we'll form a new shape, which is the stagger. Exactly. using the same molecules, so you don't get confused. CH3, H, H. So this is the staggered. Staggered is a less, more stable, meaning less reactive. So it's more stable and it's calmer. So since the molecules are not really behind each other or pushing at each other, they're just away, further away. So you understood this part of the Newman projection, correct? Now I'm going to show you, and you tell me, is this a conformational or structural isomer? Tamam? So we have a CH3, for example. Let's take a Cl, H, then we have an H, H, and then CH3. And then here we have a, CH3, H, and H. We have a Cl, CH3, which is to an H. CH3. What is this? What type of isomer is this? Who says conformers? You say conformers? You think this is a conformer?
Conformers.
It's a conformer?
Yes, I don't see the question.
Who says structural? أيوة هذول اثنين. What isomers are those two? Who says conformers? Raise their hand. Who says structural? Raise their hand. Yes, it's structural. We had it. Yeah, you want to explain it? Okay, I'll just like. All right, so we had this in our first exam, and many came out confused. They're like, "How is this possible?" Look, let's draw it in the regular aliphatic way. So we have a CH3. Let's take the CH3. CH3. The C, which is this one. Let's attach to an H. Attached to a Cl. Then you have a C. It's attached to an H and another H, and then CH3. This is for this. All right. Now let's look into the other one. Now look, صح مرات it's gonna be tough to draw it quick and you'll need to catch it in first glance. But what I did is I look at the Y first, see if they have similar Y structures. So the one that's in front, I'll see if they have similar structures. And the one that's to the back, I'll see if they have similar structures. If they do, that's definitely conformers. If they don't, that's a structural. Now let's check this one. This one has two CH3s, a Cl, and then this one has three H's. So you guys get it? So you have to look at the background, like look at the circle. See, all right, this has CH3, H, H. Oh wait, this one has H, H, and a third H. Understood this part? So this one got us in our exam, and I don't want it to get you guys. And then we have the other picture, which is the sawhorse. The sawhorse projection. I don't recall them bringing it in the quiz, however, it's still important to know because your version may be different. So we have the sawhorse. Do you guys know what a sawhorse aslan is?
Yeah.
Well, yeah, tell us. It's alright. It's a thingy, yes, it is a thingy. Now this thingy, you come in, it's like you cut wood on it. You put a wood here and you start cutting. Now this looks like a sawhorse because it's like a stand. You see, like 3 legs and 3 legs, and there's something in the middle. That's why we call it a sawhorse. Now how do we draw a sawhorse? Basically there are, let's say, CH3, H, H. This is a carbon. Keep in mind, the one in the middle here is a carbon. Alright. Then you have CH3, let's say another CH3, and then H. Now those three-legged thing, well, they're the ones that are gonna turn. Like in the Newman projection, if we see like the circle or the y-axis, the way y-shaped thing, it turns. Here, this one turns. So this one may turn this way, this one turns the other way. So they're rotating around this axis. In the sawhorse, what's different is that you could see on what axis they are rotating. فاهمين علي? So basically we can see this axis, and we can see that it's rotating on this axis. If you guys have any question, you can stop it, it's alright. Till now, no questions? Alright, so this is the overview of conformational isomers. So now, we mentioned that Hamza mentioned that there's energy levels. Alright, what are the energy levels difference? So basically you have eclipsed and staggered, and both of them have different energies. So which one we said has more energy? Eclipsed or staggered? We all agree it's eclipsed, correct? Tamam. So here, for example, you can see that you look how they're back to back. The CH3 and CH3, they're back to back, correct? So that means they are eclipsed. And this creates a torsion force, as your friend mentioned here. And this force creates a high energy. But then we see that it declines. Why does it decline? It turns to a staggered formation. You guys understand this topic?
60 degrees, yes.
Yes, Khelifi. هو بيضل يلف بس احنا what we're looking at is شو اسمه just stages يعني في مراحل كيف يكون شكله. And here at the bottom, why is it the least energy? Could one of you guys tell me? Exactly, as he said, they're spaced apart, far apart. They're all in opposite axis. Exactly. So that's why it has the least energy. Then we go back to the previous looking one, and then we go back to the eclipse. And it's just a cycle of activities. Alright, so now we go on to cycloalkanes. Before we start, you guys know what are cycloalkanes? Rings, exactly. And there are multiple shapes of this ring. So let's start with the simplest shape that we can make. The simplest formation of a ring is with 3 carbons. So you'll have to have C, 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 and you just have a triangle. So you need 3 carbons. They may ask you what's the least amount of carbons you need to make a ring. Exactly, we need 3. So cyclopropane is the smallest ring structure, and it's very rigid and highly strained. Why is it very rigid and highly strained? Do you guys remember the... Exactly, there are strains. So basically, the angles, we said what's the ideal angle? 109.5, correct? This angle in the triangle or the cyclopropane is 60 degrees, which is way less. So it makes it unstable. Now let's look into another sister of the cycloalkanes, cyclobutane. Now, they might ask you what is the least amount of carbons to have a non-linear shape. Do you guys know what a non-linear shape? So it doesn't stay in one plate. So it may move like this, move like this, move like this. So it's not flat. Cyclopropane, you can find it just flat, just a triangle, like one plane. But once you introduce one more carbon, which is a cyclobutane, you make it puckered. So it's like kind of like yeah, it's like this. So I'm not. So it's, I don't know if you guys could see it, if it's that clear. So basically there's one part or one corner that's lifted. This corner creates a better, what's it called? Way to relieve itself from the strain. It's not 109, yes? Yeah, it makes it more stable. So it's not 109.5 degrees, but still it's better or more stable than the rest. So it's still better than the rest. All right. Yeah, and it's more reactive than a linear alkane. Why do you think it's more reactive than a linear alkane? Because it's unstable, exactly. So the bonds will break, and then it will want to introduce another molecule, maybe a new carbon or maybe a halogen, and then it will form what's it called? A new product. On to the next one, which is cyclopentane. So you guys know pentane, butane. I don't have to explain it again. So cyclopentane means 5-ringed alkane. Now, as we said, the first non-linear is the cyclobutane, correct? what's the shape of the cyclopentane? It's like an envelope. So if we can zoom into the, yes. So this is how we would draw it, maybe like this, or maybe like a regular pentagon. However, the shape it's found in nature is an envelope shape. So both this corner and that corner may rise and make a shape like this, like an envelope, like closing an envelope. So this helps it relieve the strains as we mentioned before. So what are its characteristics? So it's more flexible than the cyclobutane as mentioned. Its angle is 105 degrees, so that's near the 109.5. And as we said, it has an envelope conformation. We move on to the last one, which is the cyclohexane, and it's the most, stable from these, the cycloalkanes. And in this one, when you get to the next slides, we have multiple conformations to it. Since it's 6 ring, yes.
Stable, why do we have conformations for it?
Now it is stable, however, we're going to show you in the next slides, it's not as stable as the aliphatic, regular aliphatic. Yeah, so it is stable more than the rest, however not more than an aliphatic. Alright, move on to the next slide. Alright, so, yes.
See, both the same as envelope?
Which one?
Boat and envelope, are they the same?
Oh, boat is for the yes, hexane, cyclohexane. So the boat has an additional carbon, however, envelope is just 5 carbons. So I believe that I mentioned this. We can look over to unlike conformational isomers where the atoms are located. Yes, here, do you guys think there's, oh, you have a question? Yes.
How about cyclohexane or cyclooctane?
Oh, the other ones? Now, they won't ask you much about it. However, those are the ones you're supposed to memorize, and they have their own conformation, their own shapes. Cyclohexane may change, like, since we said cyclohexane has a boat and chair conformation, the cyclohexane may have like 5 other conformations, so it's not known. Yeah. All right. You remember the conformers, correct? We said they're just they're not like structural isomers. They just differ in space arrangement. They just rotate, correct? Do you think in cycle we can rotate?
No, because no.
Yeah, exactly. It's not free. So every carbon is attached to 2 other carbons, so it's stuck into one place. I cannot twist it. And due to this, we have what we call as cis and trans. You guys aware of cis or trans? Have you heard it in school? All right. Yes, trans and cis, correct. So here, when we make a dark wedged line, that means it is facing one side. So let's say it's facing like this. When there's a dashed line like this, it means it's facing the opposite way, like this. Tamam? So since cyclohexanes they cannot move around, there's going to be that conformation. Also in cyclopropane, butane, and pentane, they may have the same thing. And by the way, for example, here it could also be to the front or to the back. Here to the front, to the back. However, when it's just a C and a C bond to other substrates or other molecules, those we call cis and trans. You guys got me, or do you want me to repeat again? So basically, if there's a carbon and another carbon attached to each other, and they have their own molecules they're attached to, or a branch they're attached to. Some, if they are on the same side, it's cis, and if they're on opposite sides, it's trans. However, if it's on this carbon, the 3rd carbon, or another carbon, the 4th carbon, then there's no cis and trans. It's just another thing. You guys understood this? What? All right. Move on. Yes.
Why the carbon can't rotate again, please?
Why can't they rotate?
Yeah, can't they rotate? Why?
Yes, so I can use my finger on this. Alright, so since here, let's say we have a C, and a C. Alright, let's forget the cycle. Let's just have them as a regular butane. Tamam? Here they could rotate because they're free. They're not attached to anything. And here they could rotate. Here they could also rotate. However, once you close this cycle, They cannot rotate on each other because then they'll have to rotate, it'll cause a chain reaction. But they cannot rotate onto themselves. So that won't be possible. You understood it? Like, let me try to get, there's a wire. Let's use this wire. So imagine this is the cyclo. We want to rotate. Watch what happens to the wire. It's just going to collapse onto itself. What if it was free like this? And then we want to rotate. It'll just rotate, rotate, rotate. If it's free, understood? All right. We move on. All right, so here's a small, what's it called? A map that shows you the types of isomers. So we said there are stereoisomer and constitutional isomers. The constitutional isomers are the ones that Malak explained, which is the structural isomers. And they're the ones that differ in structure, however have the same molecule. And the stereoisomer, they change in the arrangement of space, meaning that they're found different in arrangement of space, like the conformers we mentioned. So they may be the same, but then you rotate it, and the C is to the bottom, the other C is to the top, the H is there, and the H is that. Oh. Sure? Oh, we can get to that. I'll explain the boat and the other one. All right, so then we have the geometric isomers, which is also they change in the spatial arrangement in space. So the cis and trans, as I mentioned. So that is a geometric isomers. And this is another class that you have to worry about in, what's it called? In the stereoisomers, which is chapter 5. So don't worry about it now. I'll explain the boat and chair. So all right, chair looks kind of like this. And the boat looks like an actual paper boat. It's kind of like this. So it looks like a paper boat or a Batman cow, I don't know which one, whichever you choose. So in those conformations, we have a cyclohexane. This cyclohexane is not conformable in the way it is. So what does it do? It changes or transforms into a boat or chair conformation. So which one of those do you think is more stable? Chair. And why is that?
Because of this strength.
Yeah, the torsion strength, yes.
Because if we have too big in the boat, they will end up.
Yes, so let's say we have CH3 here and CH3 here. So they're gonna bump into each other and it's be annoying. So through the chair conformation, you'll understand that, oh, they're away, they're on opposite ends. Yes, less staring. And the boat conformation, it has two as well sides or shapes it could change to. It could flip itself. So as you can see here, it flips itself. So we have what we call this. And then we have it here. Those are the axial, axial. And then the ones that are to the sides are what we call equatorial. So when we flip them, what do you think happens to the axial and equatorial? Yeah, as you guys all said, it will flip. So when it flips, the axial becomes equatorial. So let's say this was axial once, it becomes the equatorial. This, it's going up, so axial, and to the side it's equatorial. Axial, it was once equatorial. So you guys get the trend it's going on, right? So is there any confusion on the boat and chair conformation? Ahmed. 7 carbons? Yes, it's just a drawing. بس ايوه بس they're gonna provide you with pictures so you can draw pictures. Yes. بالاكزامبل كيف جابوه ولا؟ هو زي الكرسي صح؟ يعني هون for example you could put a human being here. هاد راسه، هاد ايديه، هاد اجريه. So he's like sitting على كرسي، قاعد على كرسي. هون زي السفينة هيك many people قاعدين على السفينة. فاهمة؟ Alright.
We know that each one. ثواني. We know that each one seeks to achieve a lower or a relatively low strength shape.
Yes. Yes.
So why do we have both in nature? Why don't all boats like transfer to the chair?
Now, what's it called? Good question. Why do we have boats if it could be chairs? That's what you're asking.
Yeah.
Now, what's it called? They like to move around. There are electrons. It's not, atoms don't just stay where it is. It doesn't freeze into its position. Electrons move, protons, but the atoms move in a way. So it will come, like for example, there's a chemical reaction, cyclohexane was made. It could start off as a boat, but then it'll decide I'm not too conformable and then move to a chair. But then maybe because of movement of electrons and movement of the whole atoms within this molecule, it could go back to a boat. So it's very possible that it's just the movement of electrons. They're not always just stiff. You understand? They won't ask you about that, but I'm just explaining for your information. Ahmed.
What type of stereoisomers are chair and boat? Conformational?
Yes, they're conformers. They're the exact same molecule. It's just they're changing shape.
But do they have
Spatial arrangement. Yes.
do they rotate?
No, this is not really rotation. It's just flipping. So basically, it's like this, but then it chooses to be like this.
I understand. I'm
Yes.
just learning about the arrangement of them. What type of isomers are they?
Oh, that's a good question. No, they're.
See, they can't rotate, so they can't be conformational.
Yes, that's a good question. I think they are conformers. I think they are. Yeah. The equatorial and axial. They ask you about equatorial and axial. Then those are the only ones that are, I believe, that are conformers. Yes.
You have an answer.
Yeah. Thank you, Ahmed, for that good question. So yes.
Can you please re-ask the question again?
Yeah, he asked to what family of isomers is this? Is this structural, geometric? So this one could be a form of conformers. So in a way they just switch their orientation space. So they would go from the side and then they go to the top.
So they are confirmers.
Yes, I believe so. Yeah. If you want, they never asked us about cyclohexanes and their isomers, but if they do, they're going to usually ask you if it's what's it called, structural or cis or trans.
But I think it just be, since in the book they just say like chair conformation, so just conformation.
Yeah, most likely it's conformers, true. However, I'm saying that they never really ask us about those. They usually ask cis or trans, structural, if it's related to the cyclohexane. But that's a very good question. So now we go into chemical reactions. Do you remember how I told you that there's a trend in our organic chemistry course? They like to talk about the nomenclature, as we did, talk about the structures of it, as we did, the isomers of it, and now we move on to the reactions. So now in the reactions, there are multiple reactions. First of all, I'd like to mention that they have strong non-polar covalent bonds. Alkanes are fairly inert, so they don't react much, but they are involved as oxidizing or reducing agents. So they can be good solvents for extraction, recrystallization. So they may ask you from this slide, for example, are alkanes reactive or do they react? So you know they are mainly oxidizing or reducing reagents. So since they are just non-polar covalent bonds, they're stable. The ones usually that are aliphatic, they'll be what's it called, less reactive. All right, oxidation reaction. What do you know about oxidation reactions? Go ahead. Hands. Yes. Tema. Combustion. All right. Loss. Yes. Loss of electrons. What else? Gaining oxygens. Yes, that's the main. Yes.
Oxidation has three definitions: gain of oxygen, loss of hydrogen, or loss of electrons.
Yes, so as your friend said, it's gain of oxygen, loss of hydrogen, or gain of loss of electrons. So let's look at this picture right here. Here we have what? A methane, right? One carbon, regular what's it called? Regular carbon. They have a formula to it, but I'm not sure if you brought it in an exam. But just remember it. It's C equals to negative, and then the amount of H's. Now look, H is equal to +1. Fahmeen? So H is +1. O is -1 because it's an oxidation reaction. Any electronegative, what's it called, component is also a -1. Another carbon is 0. Yes.
Are we calculating the electronegativity or the oxidation?
Which one?
Now,
For the numbers, I think they target the electronegativity, the numbers. However, this reaction, we're talking about oxidation. Those two are not, what's it called? Just keep them to the side. However, we're gonna focus on the oxygen. So in this form, you have negative, and then you have, how many hydrogens do we have? 4. So how many pluses? Plus 4. So plus 1, plus 1, plus 1, plus 1, and it combines to a negative 4. Now here, C is equal to negative, and then how many hydrogens do we have? 3. That's attached to the carbon. So what we're doing is formulating for the carbon here. Understood? And then how many oxygen do we have?
1 minus
1. So this is a mistake, I think, in the PowerPoint. So, oh no, it's correct. So plus 1, plus 1, plus 1, minus 1. How much is that? So 3 minus 1. 2. And since it's positive 2, however, we have a negative outside, it becomes negative 2. Same goes for the Cl and NH. Now here is the most oxidized carbon. And why is that?
minus 2 minus 2.
Yes, because there are 2 oxygens, and since didn't we say that oxygen is minus 1? Exactly. Here we have 2 bonds, so we minus it by 2. So minus 2, that gives us an oxidation of plus 4. And here with the same concept. So we have 2 oxygens. One is double bond, one is not. That's minus 3 plus 1 oxygen, plus 1 hydrogen. That makes it a minus 2, but with the other minus, it becomes a plus 2. So you guys understand the flow and trend of this oxidation? Yes?
About NH2, why is it just minus 1?
Because since it's, first of all, it's more electronegative, and it has a 1 bond with it, it's considered a minus 1.
Any electronegative minus 1.
Yes, it's more electronegative, so it's a minus 1. And same with chloride. But in the exam, they just focus on oxygen. All right, now free radical processes, or let's talk about halogenation of alkanes. Now you guys know what the halogen group is, right? So it's group
The 7.
17. So if you guys need help, there's going to be a periodic table in the exam. So group 17, maybe chloride and its family. So let's say chloride, for example. So let's see, the R here is a hydrocarbon. It's multiple C's bond to each other, and then we have an H. Then we add a halogen group, and with the help of heat or light, we could substitute it for the H. So you can see here are the hydrocarbon, then we add a halogen, heat or light. We see that the halogen took the place of the hydrogen, correct?
Yeah.
What happens to the other halogen? We have to add halogen, like the gas molecule itself. So let's say Cl2. We have to add Cl2. And one Cl will go with the group, the R group or the hydrocarbon group. And then one will become bonded with the H. And this is usually an acid. So HCl or HBr, they are acids. So through halogenation, we make alkali halide, and we make an acid. So you guys understand halogenation? And then there's a free radical process, which I believe is in the next slide we'll discuss. Yes. So how is it done? Like what happens to the electrons and how are the bonds formed? So let's look at the 2 Cl molecules. Since those, we said there's Cl2, right? We take the gas form of the molecule. Cl2, so a chlorine molecule. With heat and light, they split apart, become 2 free radicals. As Malak explains, you guys know what free radical is, correct? So 2 unstable chlorine molecules are just floating around. And then we enter something we call propagation. So initiation means splitting and making free radicals for us to initiate the reaction, hence the name. Then propagation means that we're now gonna substitute or take place of the H, the hydrogen. So here you can see that an H goes with one of the Cl molecules and forms an acid, and then there's an alkali radical, meaning the hydrocarbon is just missing a part of it. Then another molecule of chlorine with the help of heat and light splits and one moves into the R and Cl and makes the alkali chloride, or it could be alkali bromide, whichever molecule they choose. And in termination, we just basically are adding, we're trying to terminate any free radicals. Because, for example, if this reaction happens in our body, this is very harmful. So we're trying to eliminate or terminate the free radicals in our body. So they conjoin. For example, 2 free Cls become one molecule, one gas molecule. 2 Rs become a hydrocarbon group. And it could be an alkyl halide, like the RCl. Now we move on. So there's another way of free radical chain mechanism. So we have now here chloromethane, and then 2Cl. So we're adding more to it.
It's depending on the
Yes.
concentration of the
So it doesn't mean that, oh, khalas, there's Cl, we just add 1 and that's it. It could add more to it. So CH3, and then we add a Cl. And then we want to add another Cl. We substitute an H. We remove an H, and another Cl. So it becomes CH2Cl. Guys. And then we add another one in place of the hydrogen. So it becomes CHCl3. And then we want to replace it all, it becomes CCl4. You understood this topic? Understood this concept? So basically what we're saying is that we're just switching the H's. Yes?
So instead of having Cl2, what if we have Br2?
Yes. Since it follows the same, so any group under the halogens family it will follow the same trend. Oh.
You see how there's an arrow in Cl2? Instead of the Cl2, it's Br2.
Oh, you mean if there's a Cl already? Yeah, it is very possible. Since it's a halogen, as I said, it could follow even if there is another halogen, which is Cl. It's which one comes to contact first. So this is just a chemical reaction. If the Br is there, it will change with the Br, and there will be a Cl. That's why we have sometimes bromochloromethane, for example. Yeah. So yes, now we enter to what's it called? Once we remove a group, you think it's going to be stable if you remove any C group from hydrocarbon? No, it's not going to be stable. Akid, it won't be stable. Now, which one of those do you think will be the most stable? The one with tertiary, or the one with more?
with more C.
Or non-removed groups, or more C's, yes. So, if it has, as we call those tertiary, and those are secondary, those are primary, and this is just a methyl group, the tertiary is most stable. And why is that? There are many, like, many C's just protecting it and helping it contain the hyperactiveness. And same with secondary, however, it's less than tertiary but more than primary. Same with primary, like 1 carbon is helping out. And methyl is just the most reactive and most crazy out of all of them. You guys understood this part? Any questions you guys could ask? No? Alright. So no questions? Yes. Eclipse was staggered? Yes, conformers for sure. And human projection sawhorse, focus on them. It is conformers بس لو ذكر لما أنا قلت were you there لما شرحت على البورد؟ أيوة. Sometimes they like to play tricks on you guys. They might change and make like 3 carbons attached to 1 carbon molecule and the rest is hydrogen. But in the other one, 2 carbon attached to the other carbons. Understood? In the shape of human projection or sawhorse, it's usually conformers. But you guys check in the exam, make sure that, oh, this is conformers. Don't just just mark it. Understood this concept? Any other questions?
How are you?
I'm good, man. انتوا كيفكم؟ لا عن جد. I know chemistry is a long شو اسمه topic and concept and you have to grasp a lot. But it's fun. I find it personally fun when you understand the concept. So the most important is not تدخلوا حافظين. ما تحفظوا test banks ترى. I don't know what as people they come and they memorize questions from Google, questions from anywhere they get, and they go in. No, memorize the concept, memorize the what's called the theories, memorize how to draw, and you'll be good. Understood?